Welcome to ashatech.com, your engineering sciences channel. In this video, we are looking at drawing the shear force and bending moment diagrams, and the beam is loaded as follows. We have a pin support here at A and a roller support at B. Then we have a uniformly distributed load that is over a span of 4 meters from support B to the end of the beam. So let us look at the solution for this problem. We will start by looking at the free body diagram and using the equilibrium conditions to determine the reaction forces. The reactions at A, we will have, since it is a pin support, we will have two reactions, one in the horizontal direction, another one in the vertical direction. Then since we have a roller support only here, we will have a vertically upward reaction force, and we will also give the uniformly distributed load in terms of its total load. Since it is over a span of 4 meters, the magnitude will be 4 times the 10 kilonewton per meter, and that will give you 40 kilonewtons, and this is going to act at the center of this uniformly distributed load. Since it is over a span of 4 meters, then it will act at 2 meters from the end and 2 meters from the support here. So it will act here. So use the equilibrium conditions to determine the reactions. Sum of forces in the horizontal direction is equal to 0, AX is equal to 0. AY plus BY is equal to 40. In other words, upward forces are equal to downward forces, and everything will give you 0. Now, if that is the case, we need to also determine the sum of moments about A. Sum of moments about A here, the 40 kilonewtons is in a clockwise direction, the BY reaction is in an anti-clockwise direction. So BY times 8, because the distance from the line of action of B and this point A is 8. Then this one from this point is going to be 8 plus 2, so it will be 40 times 10. At the end of the day, BY is equal to 400 divided by 8, which is equal to 50 kilonewtons. Okay. Now we are going to use the method of sections to draw the shear force diagram and bending moment diagram. We have got two sections wherever we have a discontinuity from the end to the other side. From here to there, we have, remember, we have a reaction here, and we have also a discontinuity due to this support here. So we will have a section here. Then when we move from here going forward, we see that we have uniformly distributed load. We can see it better here. From here, from the support to the end, we have a uniformly distributed load. So we have a discontinuity here, at this point, and therefore we will put our next section here, and that will be the end. So we have two sections, and using the method of sections, we will be able to determine the bending moment and the shear force, the shear forces in those particular sections. So let us consider a section of 0 less x less 8. That is segment 1 from 0 to 8, and we are looking at the distance less than 8. What is happening between 0 and 8? So we are calling the distance from here to the section to be x. Then we will have bending moments pointing in an anti-clockwise direction, but at the left of the beam of the section, we are calling it positive, and going downwards at this section, also pointing downwards, is the shear force, and is going to be positive. Now let us sum forces in the y direction. In the y direction, we have a force which is 10 pointing downwards. So since they are all negative, I can still cancel the negative and negative with the 0, and they become positive. So V1 is going to be negative 10 kilonewton. Then we look at sum of moments about this point. We will have the 10, which is in an anti-clockwise direction, so it will be minus 10x. Of course, it is at a distance x from the section. then minus M1, which is the bending moment at that point, but in an anti-clockwise direction too. So M1 is going to equal to negative 10x. Okay, we go to segment 2 for a distance between 8 and 12, and we said we will have a section after this support. So we have the 50. Remember, when we determine the reaction here, it is 50 kilonewtons, but the AY, remember AY here is going to be 40 minus 50. So AY, we have found out that it is negative 10 kilonewtons, meaning that the assumed direction here is wrong, and therefore that's why we were able to put it here pointing vertically downwards. And the same thing is going to happen to segment 2. So we have it pointing vertically downwards, and this reaction here pointing vertically upwards, since it agreed with the equations of equilibrium. So let us sum forces in the vertical direction. We have this uniformly distributed load, which is over a span of, remember, from here to here is x, and from here to here is 8. So from here to here is x minus 8, and therefore the uniformly distributed load is over a span of x minus 8. So since it is 4 kilonewtons per meter, then therefore the magnitude will be 4 times x minus 8, and it will act at a distance x minus 8 from here to there, or from here to there. So if we are summing forces in the vertical direction, we have negative 10 minus 4 into x minus 8 minus v2, since it is also pointing vertically downwards, then plus 50, which is pointing vertically upwards. So minus 10 plus 32 plus 50, that is 82, minus 10, that will be 72, minus 4x will equal to v2. Okay, since v2 is equal to 72 minus 4x, let us look at what is our moment. Our moment will be m2, and let us see what happens. This 10 is in an anti-clockwise direction, m2 is in an anti-clockwise direction, the 4 into x minus 8 is in an anti-clockwise direction, but the 50 is in a clockwise direction. So that's why we are saying it is minus 10x minus 4 out of 2 into x minus 8 times the distance. Of course, the distance is supposed to be x minus 8 out of 2. So plus 50 into x minus 8, because it acts at a distance of x minus 8 from the section. Then minus m2, because m2 is pointing in the anti-clockwise direction, so I'm making it negative. So this equation becomes, this is minus 2x squared, then minus 128 minus 1, that is minus 528. But what is the x values? It will be minus 10x plus 32x plus 50, so it will be plus 72x, then minus 528, and this is m2. So this is the equation for finding the bending moment between 8 and 12. Then this is the formula for calculating the shear force, or the equation for shear force between 8 and 12. Now, to draw this shear force diagram, I have drawn this using MATLAB. As I said, I will share the way how we code and produce these drawings in MATLAB in the future. So keep following my videos, subscribe, so that video does not bypass you. So here we are looking at the first segment. Segment 1 has negative 10 kilonewtons as the shear force. So I will go to the shear force, I move to negative 10. Then it is going to be a constant up to when I meet a support at distance 8. So it becomes constant up to when I meet 8. So here at 8 I will have a jump because of this point load as a result of the reaction. It will cause a jump. that goes to a magnitude of, now I will use this equation. I put in x at 8, x is equal to 8, I will see that it will go to 40. So my equation will go to almost 40, because if I put here 8, this will be 32. I subtract it from 72, that will be 40. Then I again use the same equation at x is equal to 12. This will be when I substitute in my values, it should come back to 0. Okay, because if I put in my values here, usually this curve must come back to this point 0. Then if I have seen how to draw the shear force diagram. I've said this is negative 10 and becomes a negative, of course, constant up to 8. Then from 8 going to 12, I have an equation of 72 minus 4x. So at any distance equivalent to x, I will just substitute in this equation and I will be able to draw this curve. Okay, that means I have to go and draw the bending moment diagram. The bending moment diagram also, we are saying that at x is equal to 0, the bending moment is going to be 0, and we continue, we substitute in these values at any point at 8. When we substitute in, it should give us a value equivalent to negative 80, and which will continue to a maximum of 0. So when it comes to 0 at 12, at x is equal to 12, then our bending moment diagram will be complete. And so we will see this maximum at 0. So these values are very important. For example, where you have a maximum shear force, you need the more transverse reinforcement if it is a concrete beam, a reinforced concrete beam. If you have a maximum on the bending moment diagram, then it tells you of that position that you're supposed to do more longitudinal reinforcement. So this is how we can draw the shear force diagram and the bending moment diagram. Thank you so much.